Good morning. We are here today to talk about exponents. We move on to the next chapter here, chapter 5, which deals with exponents and logs. Chapter 5, exponents and logs. Specifically today, we will be talking about exponents and their laws. Exponents and logs, which is short for logarithms. Logarithms with an I in there. So we've talked about exponents a little bit already this year, and specifically the graph, the parent graph for exponents. So let's take a quick look at that. Exponents, you often hear the term exponential growth. Anything to the 0 power is 1, so the y-intercept we know is 1. And things grow at different rates. Let's just say this, for example, is y equals 3 to the x. If I want to do y equals 2 to the x, that's going to be something looking very similar. The problem is it won't grow quite as quick. So that would be y equals 2 to the x. And of course, you can plot points if you'd want to make the graph a little more exact. Same idea here. We got another graph. This one could be y equals 4 to the x. All right, so the shape, remember, is always the same, and that was the important part with our parent graph. These three right here are 3 examples of exponential growth. If you notice, the y values are increasing. So if we look at it in a slightly different way, we have something called exponential decay. And you'll hear about that a lot in your science classes with carbon dating and different things of that sort. And here's exponential decay. So the graph comes on down like that. And this again would be a 1 here. That might be something like y equals 1/2 x maybe, or 1/3 x. And I should say 1/2 to the x, or 1/3 to the x, right? You're constantly cutting something in half, is what's happening there. So let's start looking at some examples here of exponential growth and decay. And let's see if we can think of some real-world situations where things grow. Growth, or in other terms, appreciate in value. This is not an exact science, but you can typically say that houses or property grow or appreciate in value typically. However, if in a bad economy, this stuff does depreciate, but typically something that appreciates. Oil and gas, natural resources typically appreciate in value. Again, not an exact science. This stuff is typically. How about things that decay, things that depreciate in value? Decay or depreciate. So if we're looking at things that lose money over time, there's lots of things. You could argue that. Look at this, I got stuff disappearing here. Give me a second to fix that. I'll go forward and come back. And there are T's back, and the rest of my D is back here. And look at that, both dots to my colon are there. So things that depreciate in value, a car loses value pretty quick. However, if anybody has any experience, or their parents have antique cars or something like that, cars can also appreciate. They could be up in here if they get to a certain age. What else depreciates in value? Carbon dating, as you refer to in science classes, is a type of element that depreciates. So there are certain examples that fit both, and there are certain examples that are exclusive to each individual depreciation or appreciation category. So moving on with the math behind this, we don't need to get into too much information of different real-world scenarios. But let's take a quick science example here. And we say an isotope decays by 15% each day. Decays by 15%. That means it's losing 15% of its value every day. And we're going to say there are currently 40 kilograms present right now. And now, remember, means now. Time equals 0. Nothing has happened. It's present, this instant. All right? So it decays 15% each day. It's losing 15% of its value. Think about what that means. And we're not doing the problem yet. We're just kind of thinking outside the box here a little bit. Example, if I have 100 and then I lose 15%, I have 85. And then if I lose 15%, that's 12.75 I'm losing. So I'm down to 72.25 the next time. Okay, but notice this is a difference of 15 and this is a difference of 12.75. However, both are differences of 15% from that particular day. Okay, so 15% is not linear. Percentages are not linear. If I lose 15 kilograms each day, that's linear. But if I lose 15%, since I'm taking percentages of different values, it is not linear. And you have to understand that's where the exponential piece comes into play. So think about what I'm really doing here. I took 100%. I took 100% of what I had. In this case, there was 100 of them. And I lost 15%, so I was down to 85. Then I took 15% of that new number. So I'm constantly taking 15% away from what I have. Well, if I have 100% and I take away 15%, how much do I actually have remaining? Well, I think we can all agree we have 85% of the previous day's value remaining. So this is actually a really easy equation to set up. I like to use amount, so A for amount equals, well, I'm starting with 40 kilograms as it states in the problem, and I lose 15%, which means I have 85% remaining. So my equation is going to be my initial amount times my multiplier raised to the time. How many times am I going to lose 15%? So we can now at this point answer a couple questions if we'd like. The first question will be how much is remaining after 6 days? So we can just go and A of 6, the amount remaining after 6 days, equals 40 times, well, I lost 15% each day for 6 days. And if we check our calculators, that'll come out to 15.1 kilograms. Okay, and this is 6 days of decay. Now, what if somebody's curious, like, well, what happened 6 days ago? How much was there 6 days ago before we lost all this? And that's no problem. So 6 days ago is in the negative direction, right? That ago, time happened a while ago. So I do a negative 6, and I get this value, which is 106.1 kilograms. And that was 6 days ago. Okay, so slightly different there, thinking about the negative exponent. Think about what negative exponents do. This is really, if you really want to think about exponents and what they do, this is really 40 over 0.85 to the 6. And that should make a lot of sense. If I multiply by 0.85 to get the future value, I'm going to divide by 0.85 to get the past value. So hopefully that's pretty logical to you. And the negative exponent just makes it a little easier because you think of it as in the past as opposed to coming up here in the future. All right, so that's a quick little snippet on exponents and the multipliers. And remember, we mentioned a little terminology here. This is our initial value right here, our initial value. Let's throw in a little snippet there, initial value. And hopefully remember I called this something. It's called the multiplier. Okay. In this case, it was decay, so that would look like our second graph up here, right? Is decaying. Of course, that one would have a shift. We'd start on the positive side here and come down. And of course, there's no scale, so it could look like that one if I really wanted to, except for that one. So no, it wouldn't look like that. We can get into the graphs and stuff a little later if we want to. And look at that, stuff disappearing again. So let me just bring that back here. Okay, and now our stuff has not disappeared. It's going to be one of those days, I guess. All right, so let's get into some laws of exponents. We'll do that on a clean sheet here. The laws or properties of exponents. Properties of exponents. And this is where we're going to wrap up this video. So let's just knock these guys out here. The laws and properties of exponents. Well, b is going to be the base, and x and y are just variables. So if I have common bases and I'm multiplying, then I can say that's going to be b to the x plus y. Okay, if we're multiplying our bases and their common bases, we add our exponents. A nice example would be 3 squared plus 3 cubed. Okay, confirm, is that equal to 3 to the 5th? Oops, I should put a times there, 3 squared times. So that's 9 times 27, which 180 and 63, which yes, is 3 to the 5th, 243. So it checks. You can do that with all of these properties if you would like. I am not going to, though. Well, it stands to reason that if multiplication results in adding the exponents, then division will result in subtracting the exponents, and it'll be the numerator minus the denominator. Okay, b to the x equals b to the y. Now that is true if and only if, right there, if and only if x equals y. And a couple other side notes here. B cannot equal 0 or plus or minus 1. And if you think about that, if we have 0 to the power, that's 0, so that doesn't help us any. X could be anything. 0 to the 5th equals 0 to the 4th, so x is not equal y. So b cannot be 0. If it's 1, 1 squared and 1 cubed are the same also. So again, that's irrelevant. And -1 squared, and -1 to the 4th, right? Raise a negative to an even power, you're going to get the positive. So again, that's not going to be true. So 3 little caveats to that. If you have a product, a times b raised to the x, that's going to be the same thing as a to the x times b to the x. Likewise, if we have a over b to the x, that's going to be the same thing as raising the individual pieces to that one power. And again, some things to make sure you're aware of here. B cannot equal 0, right? Because you can't divide by 0 in that case. So we got to make sure that stuff's accounted for. And you have b to the x and then to the y is equal to b to the x to the y. So when I raise a power to a power, I multiply, and I'll throw an example in for that one. If I have 2 squared and then I cube it, right, that's going to be 4 cubed, which is 64, and 2 to the 6th power is also 64, right? 6 because I did 3 times 2 right here. Okay, so you can do that as well for a little shortcut. And by definition here, this one's always important. B to the 0 equals 1. And something we talked about on the last page, b to the negative x equals 1 over b to the x. Okay, and again, b cannot be 0 in that case. B cannot equal 0. All right, so that's pretty much it for the laws and properties of exponents. And we will resume this another day. It was nice to have you back.